Totally forgot. Okay, we are being recorded. So we were talking about alkynes. So what I'm going to do is I'm going to do a very fast review of all the reactions that we have done so far, okay, on alkenes. Then we're going to kind of represent the same reactions on alkynes, the triple bonded compounds, do a few names, and then start talking about something completely different. So that's the plan today. Chem 8. I bet that the focus is going to be off again, so just let me know. Monday, Wednesday, Friday, fall 20. And today is definitely not 10. It's 11 to 2020, okay? Does it look like it's too much glare and you are having trouble seeing it, or you're fine? If there is a problem, then say something. Okay. Looks like it's not bothering anyone. Okay, so the chemistry that we have seen so far, let's pick a different alkene. Let's pick this alkene. I don't know. How about this alkene? I'm not going to spend time on nomenclature, but in your mind, think about how would you name this molecule, okay? Should it be cis and trans? Should you number it from the right to left? Should you number from left to right? What should be the name of the substituent? And how should you name it, okay? Maybe I'll help you with some color coding. Okay, so think about its name. I'm not going to discuss it right now. All right, so when this guy undergoes this reaction, okay, H whatever, let's say HF, okay?
It's blurry.
Blurry? Thank you. Okay. Hopefully it stays. When you add HF to it, or HF, or HCl, or HBr, or HI, this is what happens. I'm going to draw the compound in one color. Okay. How do you do it? Well, do not draw the double bond and add the hydrogen to one side of the double bond and add the fluorine to the other side of the double bond. That's how you should do it in the exam. H and F, or H and F. You need to know the mechanism, how exactly it happens. And you remember how we did it. We pushed the double bond to the hydrogen, the proton, produced F minus as a byproduct, and then produced a carbocation either here or here. And the carbocation, the C plus, was attacked by the F minus or Cl minus or Br minus or I minus, and then produced the products. And Markovnikov rule said that the fluorine likes to go, the anion likes to go to that end of the double bond that has less hydrogens. Okay, this end has 2 hydrogens, this end has 1 hydrogen. Therefore, this is major and this is minor. Okay, this will be produced in greater quantity. Okay, that's what it means, because it goes through a carbocation that's produced here, and this one goes through a carbocation that's produced here. We discussed it in the previous classes. Watch the videos. We learned, so the mechanism is included. Mechanism is needed. You need to learn that for this reaction, okay? The next reaction, let's talk about the next reaction. if you react it with hydrogen gas and a catalyst such as platinum or palladium, I'm just going to say CAT, okay? And you produce, can you guys mute yourselves? I can hear someone talking in the background. I'll do it. That's okay, not a big deal. That's totally fine. I like noise. You get an alkane from alkene, substituted alkane. Don't let the hydrogens bother you because this molecule is just like this. Okay? I just showed the hydrogens because they're the ones that came in. Okay? This reaction is called hydrogenation. We'll talk about the names in a second. Then the next reaction was, what color shall I use? Black. Next reaction was adding bromine. Okay, and again, the double bond disappears and the bromines are added to the double bond from two ends. Okay, and the last reaction we covered was we added a little proton, because this, unless you add the proton, the reaction doesn't go. And then we also added water. What happens in this reaction? Well, water adds across the double bond, just like it did over there. Okay, and two products look like this. You add water from H from here and OH from here, or H from here and OH from here. So let me add the OH first. OH here and OH here, and the proton is added from the other end. Which one is major? Well, the anion, in this case, this is kind of like the anionic part, that goes to the to that end of the double bond that has less hydrogens. So again, this is major. This is major and this is minor. What are the names of the reactions? In general, these reactions are called electrophilic addition reaction of alkenes. Now you know that it also applies to alkynes. Alkenes and alkynes. Okay, double bonded species. First reaction, addition of an acid. This reaction is called hydrogenation. Hydrogenation. The next reaction, they all are electrophilic addition reaction of alkenes or alkynes, in this case alkene, but there are special names. Hydrogenation, this is called bromination. You're adding bromine. And the last reaction is called acid catalyzed hydration. Acid catalyzed hydration. Okay, these are the reactions that I want you to know. It's not that difficult. All these reactions can be applied to an alkyne as well. How would you apply to an alkyne? I'm just going to kind of repeat the same reactions on this side on an alkyne. And let's draw a simple alkyne. Let's draw an alkyne. Let's draw the alkyne in blue. How would you name this alkyne? Very fast. Who is its grandfather? Alkane. How many carbons does it have? Every end and every bend is a carbon. So alkynes often confuse students in the beginning, because sometimes you don't know how many carbons are there because it's kind of written straight. But remember, the end of that triple bond, there is a carbon here, there is a carbon here. There is no carbon on this side. There is a hydrogen. There is a hydrogen, which we are not showing. Hydrogen, carbon, carbon, CH2 and CH3. So what should be the formula of it? CH3, CH2, CH, right? So that'll be the formula. So it'll be 1, 2, 3, 4, C4, H, what? Of H6, C4, H6. What is it? What is the name of it? 4 carbon means which alkane it came from. Quick, fast.
Butane.
It came from butane. So what should be the name of this particular alkyne? Ine.
Butane.
Awesome, thank you. You got it. Butane. This Y is important. Perfect, you got it. No cis, no trans, no numbering, because I almost screwed up. What was I going to screw up? I actually misspoke. Something is missing. You can have another butane. So what's missing here? Who can help? One butane. You can have 2 butane. That guy will look like this. This is 2 butane. This is 2 butane. So you need to know exactly what not to do, which I was very close to making a mistake. 1 butane. So let's go through the reactions. Same reaction. So if you add HF, let's use a different acid. Let's use HBr. Okay. If you use too much, then something will happen. So just use 1 molecule of HBr for 1 molecule of the alkyne. Okay. And that is called 1 equivalent. 1 equivalent means, I was going to use it like a metaphor, but I think early in the morning, I don't want to joke around, okay? So 1 equivalent means, it's confusing. Let's redraw this here, okay? Let me just spell out the whole thing. This is 1 equivalent HBr. That means for each molecule of the alkyne, you have only 1 molecule of HBr present. You don't have excess. You don't have too much, okay? For one hand, you have 1 glove. So you can only put 1 glove in each hand, okay? So what will the product look like? Well, one of the 3 bonds will be disappearing. Remember, 1 sigma and 2 pi's. 1 pi bond will open up and accept the HBr. So from triple bond, it'll go to a double bond at the very end. Once it becomes double bond, it's not linear anymore. Remember that. Do your mental organic chemistry. Once it's double bond, the angles are 120 degrees. So the molecule looks like this, okay? And this hydrogen is attached here. and then the bromine is attached here. Okay, that's one product. And what's here? Well, it was born with a hydrogen. We just didn't show it. This hydrogen is there. Okay, the hydrogen that the molecule came with, that's there. That's that guy. Can you have another HBr product after the addition? Of course you can. And that guy will look like, the bromine will be on the other side, and the hydrogen will be on this side. Okay, which one is Markovnikov product? Obviously this one, major. Don't forget that name, Markovnikov. Markovnikov. This is major, and it's called MARKO NIKOV. Markovnikov product. Okay, that guy. What else? What else can happen? Well, the next reaction was hydrogenation. Again, if you use just one equivalent, it is possible to add measured amount of hydrogen gas. It's pretty cool. If you add just one equivalent, EQ means equivalent, of hydrogen gas and the catalyst, palladium or platinum, not both, either palladium or platinum. Okay, what will it look like? Well, it'll look like this. From an alkyne, it'll become an alkane. And this guy will be, from one butene, it'll become one butene. Pretty interesting, right? Third reaction, if we add bromine, just bromine, you don't need anything, you don't need any catalyst or anything like that, just bromine. Okay, the bromine will be attached. Again, from triple bond, it will become a double bond. Again, let's say we use one equivalent, just one molecule per one molecule. One equivalent HBr. Then what will happen? Well, triple bond will become double bond, and the bromines actually attached from the two other ends. Hydrogens are attached. Hydrogens are always attached from the same side. Just FYI, it's not a big deal. I'm not going to test you on that, but for your information. Okay, bromines are attached from the other sides. If you ever take, if you had taken 128A or 128B, you would be learning how that happens. It's interesting. Okay, so one bromine attaches itself from down here, other bromine attaches itself from up here, and the hydrogen that it came with, it's right there. And the last reaction was hydration and using a little bit of catalyst, catalytic, 1 drop of HCl or 1 drop of sulfuric acid will do it. Just a little bit, just like a little catalyst, because catalyst means as the reaction goes on, the catalyst starts the reaction. As one cycle ends, the catalyst is regenerated again. So at the end of the day, you get your 1 drop of HCl back. Okay, it's not possible physically to extract it back or recover it, but catalyst means it keeps getting regenerated. So what else is there in this reaction? Catalyst plus water. And what happens to the double bond, triple bond? Well, the triple bond becomes double bond, just like any other reaction. And the triple bond is hydrated. Okay? The proton is added in one reaction to this side, and the OH is added to the reaction on the other side, and it came with this hydrogen. Don't get confused that why did Dr. Mitra or why did Shantanu leave that place empty? Well, it's not empty. Sometimes we just don't write the hydrogens. These are important because these are the incoming groups. You're adding the proton, you're adding the water's OH. So that's why I'm drawing them. Sometimes I may just leave the molecule like this. That doesn't mean there is nothing there. That means there is a hydrogen there. Okay, I just didn't write that hydrogen because sometimes it's overwhelming to write every hydrogen and every carbon. So don't get confused. What's the other molecule? Well, the other molecule is the OH is added in the middle. OH is added here, and the H is added there. Well, which one is Markovnikov product? Which one is the major product? Where the OH is added to that end of the triple bond, which has less hydrogens. Which one has less hydrogen? This end has no hydrogen. This end has one hydrogen. So it'll prefer this one. So this is going to be your major product. Okay, and this is going to be your Markovnikov product. Markovnikov product. This is the Markovnikov product. That's not the Markovnikov product. So this pretty much ends our discussion of alkene and alkyne to the end. I'm keeping it very simple as possible. Usually I teach a little bit more, but then I don't want to compare. This is special time, and this is fine. There is already a lot of information for you guys to soak in. Okay. 4 reactions: addition of HF, or HBr, or HCl, or HI. You need to know the mechanism, how it happens. Pi bond grabs the proton, produces a carbocation either here or here. One of them is better than the other. And then the F minus or Cl minus or the Br minus or the I minus attacks the carbocation, produces this halogenated compound, fluoroalkane. Okay, that's reaction number 1. Second reaction is saturation. When you have some holes, double bonds are kind of like places where there are not enough hydrogens. Double bonds can take more hydrogens. Triple bonds can take even more hydrogens. So they are unsaturated. Unsaturated. This is completely saturated. It can't take any more hydrogens. So this reaction is also, sometimes we refer to as a saturation reaction. You're saturating saturated fat, unsaturated fat. Now you know what is meant by trans fat and cis fat. Trans fat is bad, cis fat is not so bad, saturated fat is really bad. I don't want to get too distracted. Maybe one of these days before we end this semester, this interesting semester, we will talk about that. Maybe someone can mention. If we ever finish like 10 minutes early, we can discuss it. You should know that, okay? But you can, now at least you can relate to those terms. Saturated fat, unsaturated fat, trans fat, cis fat. So trans fat has trans double bonds like this. Cis fat will have cis double bonds in the fatty molecule, okay? Bromination and hydration. This reaction is acid catalyzed hydration. They're all applicable to the alkynes, but provided one reaction happens when you add just one equivalent of HBr, just one equivalent of hydrogen gas, just one equivalent of bromine, just one equivalent of water and H+. Okay, if you add too much bromine, if there was one more molecule of bromine, you know what will happen. This double bond will disappear and it will form a tetrabromo compound. Another bromine will enter here, another bromine will enter here. The leftover pi bond will disappear. If you add one more hydrogen molecule, well, from butene, it'll become butane. Simple as that. This is kind of like that reaction. Okay, now you just made, from the grandchild, you made the daddy. Okay, and the daddy reacts one more time with hydrogen gas and palladium, it forms the grandfather. Butane butene, butyne. Got it? So if you react with excess or two equivalents of HI or HBr or bromine, it'll just add one more time. And the double bond will disappear, will become single bond. What time are we doing? 8:26. Okay, I need that time. The nomenclature of alkenes and alkynes, I'll keep it to the simple, to the minimum. Okay, it'll be very simple. No need to panic. What else? Yeah, these reactions, cis and trans, when it's applicable. When it's not applicable, then it's not applicable. You know the hybridization, sp, sp, sp3, sp3, all the bond angles, 109.5, 109.5, 180, 180. Don't screw up the number of carbons in a triple bond. There is a carbon here, there is a carbon here, there is a hydrogen here. We haven't written that. Remember that. If I just write it this way, then there is a hydrogen here, two hydrogens here, 120 degrees, sp2, sp2, flat. This part of the molecule is flat. This carbon, this hydrogen, this carbon, and these two hydrogens. 1, 2, 3, 4, 5, 6. Those 6 items, 6 species are planar. Not necessarily this methyl group and this methyl group, because this CC bond can rotate. So it will go through different conformations. Sometimes the green guy will be up, the purple guy will be down. Sometimes the purple guy will be up, the green guy will be down. They can spin around. So remember that, what we practiced. Single carbon-carbon bonds can rotate. Carbon-nitrogen bonds can rotate. Carbon-oxygen bonds can rotate. Double bonds cannot rotate. Okay? Once you have a double bond, it's locked. Cis and trans, it doesn't matter, because you've got two same things on the same one end of the double bond. You have to have large and small on one end of the double bond, and large and small on the other end of the double bond. You have to have different things attached to the end of the double bond. Imagine there is a double bond across my chest, and there are two things attached to the left side, two things attached to the right side. If the two things attached to the right side are same, then you can't talk about cis and trans, because it makes no sense. Because if you swap them, it's the same thing, hydrogen and hydrogen. So by placing this hydrogen up and this hydrogen down, it doesn't make it look different. Same thing is applied to if you have two methyl groups, CH3 and CH3. Again, by swapping the CH3 groups, it won't make it look different. So it doesn't matter. At that time, you cannot call it cis and trans. It's not always hydrogen. As long as it's the same group, cis trans makes no sense. You have to have something different. Hydrogen and a methyl, methyl and an ethyl, ethyl and an isopropyl, isopropyl and a propyl, butyl and a sec-butyl. Yes, cis trans makes sense. If you have a methyl and an ethyl and a hydrogen and a methyl, yes, cis trans will make sense. So use your judgment. Just the reactions of these molecules, okay? So we can take like a half-minute break, and we're going to start talking about stereochemistry. It's my favorite subject, probably not going to be your favorite subject, but some of you might like it. So let's have a positive attitude and see how you guys do it. I'm going to keep it to the minimum. Usually the way I teach it, I spend like three classes on stereochemistry. That definitely I'm not going to do that. Maybe today and Wednesday, that's it. And then hopefully Friday, we can start talking about something else. I'll keep the stereochemistry to the minimum discussion. It's important because the whole world might appear differently after you learn stereochemistry. Seriously, I'm not kidding. You probably already know much of this stuff, but you probably haven't really thought about it. Okay? All right, let's clean up the board. This is a pretty cool topic. I think many of you will like it. I usually do a very, very long and stretched introduction. I'm not going to do that today. I'm going to keep it short and simple. Well, when I say that, I don't know if that's going to really happen. I hope I don't drag too much. I'm not planning to. Let's clean up the board a little bit because I really want a clean board. As long as we can kind of introduce this concept today, I'll be happy. We don't have to cover everything. All right, let's see. I lost one of my cups. It almost looks like for taking samples by a pathologist. Okay, stereochemistry. Exclamation mark. Anybody knows what stereochemistry is? Any idea? No idea? It's important because it has to do with symmetry. It has a lot to do with symmetry. Okay, symmetry means something that has, how can I say it? Part of it is kind of like a mirror image of the rest of it, okay? We'll explain it in a second. Symmetry means like if I draw a rectangle, it's got symmetry, right? It's got symmetry because if you think about the left side and the right side, they're pretty much the same, just mirror image, right? This half, left and right, they look pretty much the same. So if I draw, stereochemistry is a fascinating subject because if you look at the world, when you get out of your house or look inside your house, and you will find lots of things that are symmetric, lots of things that are not symmetric. So it has a lot to do with geometry. I loved geometry when I was a kid. And I don't know, I mean, I like stereochemistry. I can see molecules from different angles. But again, it depends on how our brains are wired. I always use this analogy that I get the molecules, but when it comes to driving on roads, I love driving, but navigational skills are horrible as far as I'm concerned. I can't even figure, I mean, sometimes I literally look at the sun and see if I'm going in the right direction, and I still manage to screw up. I'm terrible, okay? So the top and the bottom are very similar, right? So it's got symmetry. It's got symmetry. If I draw a circle, it has innumerable symmetrical lines or planes. So this half and this half are identical, okay? If I draw a line like this side and that side, they're identical, okay? So you can, it's tremendously symmetric, okay? So if I draw I don't know, a pentagon, does it have symmetry? Let's try. What if we draw a line from here and left side and right side, they look like their mirror image. If you put a mirror, the reflection of the left side will look like right side of the half of the pentagon. So this is symmetric. This is symmetric. All these things are symmetric. So if you have letters, right? Let's start with a bunch of letters. The letter A. Does it have symmetry? Yes or no? Anybody wants to pitch in? If you draw a line from here, the left side and the right side, yes, symmetry. If I draw a letter B, does it have symmetry? Well, let's draw a B with
It's blurry.
Thank you, Javier. We just wanted to play with our patience. If I draw a letter B, well, is there symmetry? There is symmetry. Top and bottom. There is symmetry. Let me draw another letter. J, as in Javier. His name is showing up on the screen, so I thought about the letter J. Does it have symmetry?
No.
9. It doesn't have any symmetry. Sorry, Javier. It's a good thing, it's not a bad thing, okay? So it doesn't have any symmetry. The letter, tell me another letter that doesn't have symmetry. Go through the alphabets, A, B, C, D, E, F, G,
Z.
G. No symmetry. How about F? Does it have symmetry? Nope. So you get the point. So the point is that internally the molecule can have symmetry. For example, this stick has symmetry. Okay. The left and the right are pretty much identical. My mask has symmetry. Left and the right are symmetrical, right? So what happens, how do you figure out symmetry? There is also another way you can test their symmetry by placing them in front of a mirror, okay? So let's say we have a mirror. Let's say we have a mirror. This means the left side is shiny side and the right side is the, where you have the plating, whatever the coating is. Okay, this is where you stand and you see a reflection. So if you see this shape here, you will see a shape here. This is what you see. This is the object, and this is the mirror image. Okay, identical. Your conclusion is identical. If you put a hexagon, you see its mirror image, a hexagon, they're same, identical. If you put the letter A, you see its mirror image A, same, identical. I'm just going to say ID, okay? If you put the letter B, you see its mirror image B, and this B and this B, they're same, identical, okay? So when you have an internal symmetry, this guy doesn't have and this guy doesn't have, okay? And imagine, is it blurry? No, it's okay. So if you see two objects that are not mirror images, okay, then you will have trouble, you will have difficult time putting one on top of the other. Okay, I'll explain what it is. I'm missing my, I used to have like a little plastic cup. I have one. My second one is missing. I think I threw it away. So I can pull up that experiment. How can I do it? I don't think I can do it. I'm going to bring it back on Wednesday. But before, what else can we do to pull it off today? Okay. Let's get to the real point. So the point of the matter is, I'm looking for two identical objects. You know what? I'm going to sacrifice a couple of these balls. Okay, too bad. You'll have to sacrifice yourself today. These are old molecular model set. They're in pretty bad shape. Okay, death of a model set. So as you can imagine, if I put this ball on the left side, and if I look into the mirror, it'll look pretty much the same. Okay, so just imagine okay, they're same. Again, they're identical. Identical. This guy and this guy. If this is the mirror image of this one, they're pretty much the same. If you could take a computer and superimpose one into another, they will kind of mesh into each other. They will look like the same thing, right? You can do a 3D image in a computer using different program or app, and you can put one into the other, right? It's hard to do it in reality because the matter objects cannot go inside the other one, right? But in computer, you can do that in the virtual reality. So you can put it in one in the other. So now let's examine. So imagine, you can actually imagine, I'm really going to ruin this guy, okay? If I drew a letter A, okay, I can only do it once. If I drew a letter A, I need 3 more fingers. If I drew the letter A, held it in front of the mirror, what I would see inside the mirror as a mirror image will look like this. So this is the real object on your left, and this is the mirror image. Make sense? Right? They're the mirror images. If I try to superimpose one into another using a computer, you can imagine, you can close your eyes and you can imagine that one is superimposing with the other perfectly. Does it make sense? Can you guys see that? If I could put this ball with an A written, same size, same font, same style, same location, everything is the same color. If I could put this one into the other one, you know, using a computer program, they would pretty much like sync into another. They would become one. Okay, there would be no place where it's not going to be overlapping, right? Make sense? Now, having done that, let's draw a different letter. Some other letter that's not symmetrical. So let's draw a G. I just drew a G. If I drew a G here, I'm really struggling with my fingers now. But why can't I let go of my pens? I got some problem, man. Okay, the other G, the mirror image would look like this. I got major problems. I need to go see a psychologist. Just imagine this is drawn pretty badly, okay? If this is the mirror image, if this is the mirror image of the G, now one G is like this, the normal G, and this G, just imagine I drew it pretty badly. This G is the reflection of the G inside the mirror. It's just imagine it's done really poorly. Okay, just imagine that the G is like this, and then you have the bar at the bottom, right? So now if you try to superimpose one into another, you can clearly see that they are not superimposable. Got it? That means these are different objects. So once you break the symmetry, because G doesn't have symmetry inside, when you have one G written on a round sphere, and its mirror image is on the other side on another sphere, they are different objects. Okay, so if I have the G written here, I'll try to do it better here. If I draw a G here, okay, these two objects are not same. That's what I'm trying to make. That's the point I'm trying to make here. They are not identical. And this is a huge deal. So they're mirror images. What's their relationship? Well, they're mirror images, but they're not same. They're definitely mirror images. They're mirror images, but they're different. Now let's go back and look at ourselves and see what's going on here. From your perspective, let's say this is my left hand. This is my left hand and this is my right hand. From your perspective, thumb, forefinger or index finger, middle finger, ring finger, and pinky, right? If I look into the mirror, if this guy looks into the mirror, this guy will look like this, pretty much, right? With small changes, and I have some cuts when I was working on the car. I got a bunch of cuts on my right knuckles. I don't have so many cuts on my left hand because I'm right-handed, right? So if I try to superimpose one on top of the other, they don't superimpose. This is not superimposing. This is cheating, because you're not keeping the palms on the same side. You're placing the palms, one on top of the other. This is not right. When you're trying to see if they're identical objects, you have to keep everything in same perspective, same direction. The upper side of the palm must be this way, my direction. The inside of my palm should be toward your direction, and then everything should fall into place. My thumb should fall into another thumb. My index finger should fall into another index finger. It's not working. Thumb and pinky, index and what do you call? Ring finger, middle finger and middle finger, but they're a little different because it's not in the same direction, right? The left side of my right finger and the left side of my left finger, they're on the same side. It's all screwed up. Pinky and index finger. So they are the relationship between my two hands, two palms with 5 fingers each. They're mirror image, but not identical. They're different objects. Left eye and right eye, left ear and right ear, left foot and right foot, our body, if you think about it, other things, if you think about gloves, the one glove and the other glove, the mitten or the socks, there is no symmetry in the sock. There is no symmetry in the shoes. There is no symmetry in other things, like, I don't know, what else can I think about? Anything that doesn't have internal symmetry will have this problem, okay? Lefty and the righty, okay? So does it apply to molecules? Where are we with time? 8:51, too bad. We'll catch up on Wednesday, okay? We'll continue this discussion. We'll try to finish stereochemistry on Wednesday and start a new discussion on Friday, okay? Have a good day, guys, and talk to you soon. I'll take a picture of the board. Bye, everybody.